Alright, so today we're looking at differentiation. So what is differentiation? Differentiation is the process of finding the derivative of a function or the rate of change of a function. What is rate of change, you may ask? That is what is known as gradient of a function. Alright, and why do we then go ahead and differentiate? Well, if you were to think about the equation of a line, we know that the gradient of a line is what? Constant. And so y equal mx plus c, m is the gradient. And so we can find the gradient of the line by, we know that value for m, whatever that is, that's the gradient. However, for a curve, it is completely different, because let us draw it and look what we're talking about. So let's say we have the line y equal to 2x plus 3. We have the line y equal 2x plus 3. The line y equal 2x plus 3 looks like this, right? And it passes through the point 3. So this is the graph of the line y equal 2x plus 3, right? Now, the gradient of this line, the gradient m is equal to 2, alright? And so the gradient of the line is 2. Now, if you were to consider a curve, let me consider a curve. If we have that curve, look at this curve. So we have a curve right there. How would we find the gradient? Well, clearly, remember from gradient, how we find gradient, right? To find the gradient of this line, we would take 2 points on the line, right? And then it's y2 minus y1 over x2 minus x1, right? And that gives you the gradient. Now, how are we going to do that with the curve, right? We cannot do that with the curve. Think about it. Right here, if we take a point right here and a point right here, right? Then look at this. That's a line right there. Then this will give a different gradient from if we were to take the point. Let's say we want right here and right here, right? Different gradients. The gradient of a curve is different everywhere, right? And so the only way for us to find the gradient of the curve is they came up with a process known as differentiation. Differentiation allows us to find the gradient at any point on the curve. That's what differentiation do. So let's look at how we do that. Alright. Now consider I give you this curve, right? I'm going to give you a curve. Let's look at the curve of x squared, y equal x squared. That's a simple one. So consider y equal x squared, right? Now look at this curve now. So the curve of y equal x squared looks like this. That's the graph of y equal x squared. Alright? This is the graph of y equal x squared. Now let's say we want the gradient of the curve at some point, because the gradient of a curve varies at each different point. So the gradient here is going to be different from the gradient here, different from here, different from here. How do I know that? To find the gradient at a point, we have to find the gradient of the tangent at that point. You might wonder, what do I mean by tangent at that point? Alright, so if I wanted to find the gradient at this point right here, right? If you were to draw a line that passes through the curve only at that point, then this would be the gradient of the curve at this point. Alright? Now right here, when x is 0, then the gradient right here is going to be 0, because then the gradient at that point would just be a horizontal line, and we would have learned that the gradient of a horizontal line is 0. So the gradient at this point is 0, but let's say we want the gradient at this point. So to find the gradient at this point now, we will need to find the gradient of this line. So now look where I'm going with this now. Now if you were to consider a point that is extremely close to this point, so I'm going to call this point, let's call this point A, right? So we want to find the gradient at the point A. So if we want to find the gradient at the point A, right? Now let's consider a point very close to A, right? So let's consider a point very close to A, right? Let's say the point is this. So we'll magnify it now. So I'm going to magnify this graph. So magnify the graph now. So magnify the graph, and let's say this again is A. And this point very close to it, will magnify the graph so it looks somewhere like right there, right? And so we want to find the gradient of this line, right, passing through these 2 points. Alright, so now this is the point A, and so f of A now, we need f of A, and f of A is, we'll put it into x squared, so this is now A, and so the corresponding y value is f of A. Alright, now this value right here is going to be less than A, but it is close to A. So let's say because it's less than A, but close to A, then this point is going to be A minus H, where H is the distance between this point to A. So this is the distance between, this is the distance H. Alright, so that's the distance H. Alright, so now that this point is A minus H, then the functional value right here is going to be f of A minus H. Alright, now because this is close to A, alright, what we're going to then do to find the gradient is, remember this is very close to it, so let's put this in bracket, that H is approaching 0. H is approaching 0 means it is very close to A. Alright, so this point A minus H is very close to A. We just magnify the graph. And so what happened then is the gradient of this curve at the point A and so the gradient of a curve at a point, we call it dy by dx. The first derivative, dy by dx, that's what we call it. And so we call it dy by dx. And so what we're getting is that dy by dx is equal to, since it's very close to A, then it's equal to the limit as h approaches 0 of f of x minus f of x, not x, this is dy by dx for the point A, right? A. So it's f of A minus f of A minus h over, this is now A minus h, A minus h. Now, how did I get that? Remember, it is y2 minus y1 over x2 minus x1. And so dy by dx is going to work out to be equal to the limit as h approaches 0 of, now f of A would be, we'll plug A into the function which we said was a quadratic x squared, and so plugging A into that we get A squared minus A minus h all squared divided by A minus h. The A minus A becomes 0, and the minus become plus. Alright? And so this becomes over h. And so this is known as the definition of a derivative. This is known as the definition of a derivative. And so how we write that then is that hence for any function the derivative dy by dx is equal to the limit as h tends to 0 of f of x plus h minus f of x over h. This is known as the definition of a derivative. Alright, this is known as the definition of a derivative. Alright, so we'll be using this a lot when they say find the gradient of a function using the definition. Now this is the definition of a derivative. dy by dx is equal to the limit as h tends to 0 of f of x plus h minus f of x over h. So if you don't want to remember nothing so far, this is the most important thing to remember. This is the definition of a derivative. Alright. Now, there's a rule in order to differentiate now. There's a rule, and in order to differentiate, this is the rule that we follow. So if y is equal to ax to the n, this is how we differentiate. Then the derivative of y is dy by dx is equal to this n. What we say is we carry down the power, bring down n, then write back your ax, then we subtract 1 from the power, so subtract 1 from the power n, and that's it. That's how you differentiate. So y equal ax to the n, then we carry down 1 from the power and subtract 1 from the power. So let's look at some examples. Example, y equal to 5x cubed. If y is equal to 5x cubed, then dy by dx is equal to, we carry down the power, 3 times 5x, and we subtract 1 from the power square, and so dy by dx is 15x squared. So that's dy by dx. Now remember we said that when we differentiate, we get the gradient, right? And so if you were to imagine we have a straight line. We have a straight line, y equal 2x plus 3, right? And so see it here now, dy by dx is equal to, now 2x plus 3, what is this saying? Now this is really 2x to the first power, and so we carry down the power 1, then we subtract 1 from the power, so we get 2x to the 0. Now x to the 0 is what? 1. And so this works out to be 1 times 2 times 1, which is 2. Now this is really, anything without x is really 3x to the 0. And so this part is really plus. We carry down the power 0, and 0 times anything is 0. And so this shows that the gradient of the straight line works out to just be 2. So dy by dx is equal to 2. Notice that it's a constant gradient. Alright, because we just get a number. Anytime you just get a number, it is a constant gradient. And this verifies that the gradient of that straight line is 2. We could have just looked on it and just tell that the gradient is 2, right? But this is how we actually do it, using differentiation. Alright, now there are many more rules. This is just the general rule that we use for differentiation when you have a single term. Now we're going to look at the rule for differentiating sums and product. Now to differentiate the sum and differences of more than one term, we differentiate each term and then put back the plus or the minus, then differentiate the other term, then differentiate the other term, and differentiate the other term. That's how we differentiate sums and differences. So let's look at some example. Alright, so here's a typical example. Let's say y is equal to 5x cubed minus 3x squared plus 4x minus 1. That is y. So in order to find the gradient right here, then dy by dx is equal to, we carry down the power, so bring down 3, times it by 5, that becomes 15. Then we subtract 1 from the power, that becomes 2. Now we have 3x squared, so we carry down the power, so we get minus 6x, subtract 1 from the power, plus, this is really 4x to the 1, so we bring down the 1, 1 times 4 is 4, and then we get x to the 0. X to the 0, as we know, it is 1, so we can just put plus 4. Then we have minus 1 right here, so this becomes minus, this is really x to the 0, so we carry down the power, 0, and 0 times anything is 0. So we can now write the minus 0, we'll just leave it as that. So that's how we differentiate sums and product. Notice that we were subtracting here, then adding here, and subtracting here. So that's the rule for differentiating sums and differences. Now, let's look at differentiating a product. To differentiate a product, we use what is known as the product rule. So the product rule is, if y is equal to u times v, so this is u and this is v. If y is equal to u times v, then dy by dx is equal to u dv plus v du. That's the product rule. So whenever you're differentiating a product, if y is equal to u times v, then dy by dx is equal to u dv plus v du. That's known as the product rule. So let's apply this to a question. Example, let's say y is equal to x plus 2 times x minus 3. Y is equal to x plus 2 times x minus 3. So the first thing you're going to do is let u equal x plus 2. Let u equal x plus 2. U equal x plus 2 and v is equal to x minus 3. And so what that tells you then is that du is equal to, when we differentiate x, we carry down the power, which gives us 1. Then we subtract 1 from the power, so we get 1 right here. So this is 1. Now, when we differentiate 2, we get 0, so the differential of this is 1. Now, v is x minus 3, and so dv is equal to, when we differentiate x right here, we get 1, because we carry down the power 1, subtract 1 from the power. Then we differentiate minus 3, we get 0, and so dv is 1. So then now we write dy by dx is equal to, dy by dx is equal to u dv, this is u, and we're going to multiply it by dv. So we have x plus 2 times 1 plus v du. So it becomes v, which is x minus 3, v times du. And du right here is 1. And so dy by dx works out to be x plus 2 plus x minus 3. So that works out to be x plus 2 plus x minus 3, which works out to be x plus x is 2x, and then 2 minus 3, 2 minus 3 works out to be minus 1, negative 1. And so dy by dx is equal to 2x minus 1 when y is equal to x plus 2 times x minus 3. And that is how we use product rule. Alright. Now the next one we're going to talk about is quotient rule. What is quotient rule? Quotient rule is when you're going to be differentiating a function that is given as a quotient, or what we know as known as rational functions, right? And so the rule, quotient rule, is if y is equal to, this is how I like to remember it. If y is equal to t over b, if y is equal to top over bottom, I like to remember it that way. Top over bottom, top over bottom. Easy to remember. If y is equal to top over bottom, then dy by dx is equal to, you always start with the bottom. So you start with the bottom, which is b, times the differential of the top. So it's b times dt minus the top times the differential of the bottom over the bottom square. So that's what I like to use to remember it. You start with the bottom times the differential of the top minus the bottom. Start with the bottom times the differential of the top minus the top times the differential of the bottom over the bottom square. So you start with the bottom and you end with the bottom square. It's a funny, nice, and easy way to remember it. You start with the bottom and end with the bottom square. That's the quotient rule. Easy. So let's look at an example. So let's say y is equal to 2x minus 3, and it is divided by x plus, let's say it is divided by x plus 7, right? So 2x minus 3 divided by x plus 7. So we want dy by dx. So first thing we have to write down our top. So the top is given by 2x minus 3, and so the differential of the top is, carry down the power, subtract 1 from the power, and we'll get 2. Now the bottom is equal to x plus 7, and so the differential of the bottom is equal to 1. Alright, and so dy by dx is equal to, you start with the bottom, which is x plus 7 times the differential of the top. We differentiate the top, we get 2 minus the top, 2x minus 3 times the differential of the bottom, which is 1, over the bottom square. That's dy by dx. The only thing left to do is simplify the numerator, which we can. And so we simplify the numerator to get x plus 7 times 2. That is really 2x plus 14. So that's 2x plus 14. And then right here we have 2x minus 3. But then a minus is in front of it, and so it becomes minus 2x plus 6. So it becomes minus 2x. Let me make a little more space here. So it becomes 2x plus 14 minus 2x plus 6. And that is being divided by the bottom square, which is x plus 7 all squared. And so the final answer works out to be 2x minus 2x. Now 2x minus 2x, that is 0. And then 14 plus 6 is 20. So the final answer works out to be dy by dx is 20 over x plus 7 all squared. That's dy by dx. dy by dx is 20 over x plus 7 all squared. And so that is looking at products and quotient. Now the next rule that we're going to look at is known as the composite rule, or some people call it the chain rule. Composite or the chain rule. So the chain rule. So if y is equal to, this is it, if y is equal to a function of x, we have an inner function of x, right, raised to the n, then dy by dx is equal to, we bring down the power n, then we subtract 1 from the power, so we write n minus 1 times the derivative of the function inside the bracket, which we're going to call as f prime of x. F prime of x means the first derivative of the function f. And so this is the chain rule. This is known as chain rule. This is chain rule or the composite rule. So here's an example. Example, if y is equal to, let's say y is equal to 3x plus 2x squared minus 1 cube. So to find the derivative of this, it's equal to dy by dx is equal to, we carry down the power, we get 3. We then subtract 1 from the power. So right back our 3x, 2x squared minus 1. We subtract 1 from the power to get 2. But then we're going to times it by the differential of what's inside this bracket. The differential of what's inside this bracket is the differential of 3x. Now the differential of 3x is 3. And then the differential of 2x is, we bring down the power to get 4. Then we subtract 1 from the power to get x. And so it is times 3 plus 4x. And so that's dy by dx. So if you want, you can simplify this. Often the question will ask us to simplify. So to simplify, we can just multiply 3 times 3 right here to get 9 plus 3 times 4x right here is going to give us 12x. So we have 9 plus 12x times 3x plus 2x squared minus 1 all squared. And that is composite rule or chain rule. Alright, that is one way we use composite rule or chain rule. Later on, you're going to see another chain rule, which is pretty much similar to this. Alright, and so this is how we use chain rule. Alright. Now remember, we said that when we use differentiation, the whole process of this is to find the gradient. The whole process of doing all of this is to find gradient. Remember that. So we're going to be using all of these rules that we're learning eventually to find some gradient of some curve, right? Alright, just to point that out for clarity. Alright, next thing we're going to look at is trigonometric differentiation. Yes, so we're going to be looking at how do we differentiate trig functions. Alright, so these are the rules that we have to follow. So if y is equal to the sine of a function of x, if y is equal to the sine of a function of x, then dy by dx is equal to, when we differentiate sine, we get cosine f of x times f prime of x. This right here is f prime of x. So that's how we differentiate the sine. To differentiate cosine is absolutely the same thing but with a minus sign. So if y is equal to cosine a function of x, then dy by dx is equal to minus sine f of x times f prime of x. That's how we differentiate cosine. Then the next one to look at is tan. How do we differentiate tan? If y is equal to tan a function of x, then dy by dx is equal to sec square f of x times f prime of x. That's how we differentiate the tan, right? So if y is equal to tan f of x, then dy by dx is equal to sec square f of x times f prime of x. Alright? And that's how we find the derivative of a tan function of x. Alright, now of course let's look at some examples. We always want to do examples. So let's look at one example for each. Alright, so examples. Let's say y is equal to the sine of 3x minus 1. Y is equal to the sine of 3x minus 1. Then dy by dx is equal to, when we differentiate sine, we get cosine 3x minus 1 times the derivative of what's inside this bracket here, or function of x. When we differentiate 3x, we get 3. When we differentiate minus 1, we get 0, so let's times it by 3. And so dy by dx is 3 times the cosine of 3x minus 1. Alright? And that's an example differentiating sine function. Alright? Now, let us say that we have a cosine function now. So let's say y is equal to the cosine, y is equal to the cosine of 3x squared plus x minus 3. So let's say y is equal to the cosine of 3x squared plus x minus 3. Then dy by dx is equal to, when we differentiate cos, we get minus sine of 3x plus x minus 3 times the derivative of what's inside the bracket. Now the derivative of 3x squared plus x minus 3 is, when we differentiate 3x, we bring down the power, bring down 2, 2 times 3 is 6, so we get 6x. We differentiate x, we get 1, and so this works out to be minus, keep the minus sign, minus of 6x plus 1 times the sine of 3x squared plus x minus 3. So that's how we differentiate, keep the bracket, that's how we differentiate a sine function. So differentiate the sine function, we get minus 6x plus 1 times the sine of 3x squared plus x minus 3. That's how we differentiate the sine function. Now, let's say we're going to be differentiating a tan function now. So we're going to be differentiating a tan function. So let's say y is equal to, let's say y is equal to the tan of, y is equal to the tan of 3x minus 1 all cubed. Y is equal to the tan of 3x minus 1 all cubed. Then dy by dx is going to be equal to, when we differentiate tan, we get sec squared. So differentiate tan, we get sec squared 3x minus 1 all cubed. times, we need to differentiate what's inside this bracket here. Now, to differentiate inside this bracket here, we have to use two things. We have to use composite rule right here. So we have to say times. Now this 3x minus 1 all cubed. To differentiate this, we bring down the power. Then we subtract 1 from the power to get square. Then we times by what's the differential inside of 3x minus 1. And the differential of what's inside 3x minus 1 is 3. So this one is very lengthy. And so what this works out to then be is dy by dx is equal to 3 times 3x minus 1 all square times 3. Then 3 times 3 is 9. And so this works out to be 9 times 3x minus 1 all square times x square 3x minus 1 all cubed. That's the derivative of this tan function. It looks lengthy, but it's very easy. Alright? And these are the basics. How we differentiate tan, cosine, and sine. So the next thing that we're going to be looking at now is, as we said, finding the gradient of a curve at a particular point. Alright? So that's generally why we do differentiation. Alright? Alright. So now let's go back to some basics that we know about gradient. We know that when the line shape, when we're looking at gradient of a line, when the line was this way, we said that the gradient is positive, right? We know that when the line goes this way, we say that the gradient was negative. And when we have a horizontal line, we said that the gradient was 0. And when we have a vertical line, we say that the gradient is infinity or undefined. Alright? That's what we would say. Now, in terms of differentiation, for the gradient of a curve, so for curves now, the gradient at a particular point, we say that dy by dx is greater than 0, and that is when the gradient is positive at that point, when dy by dx is greater than 0. Now dy by dx, when dy by dx is less than 0, we say that the gradient is negative. Alright? Then when dy by dx is equal to 0, we say that the gradient is stationary. The gradient is stationary. So this is stationary. This one is very important. So we say that the gradient is stationary when dy by dx is equal to 0. Then when dy by dx is equal to infinity, when dy by dx is equal to infinity, we say that the gradient is undefined. We say that it is undefined. So whenever you find that the gradient of the curve is greater than 0, we say it has a positive gradient. Whenever dy by dx is less than 0, we say that the gradient is negative. Whenever dy by dx is equal to 0, we say that it is stationary. Whenever dy by dx equal infinity, we say that it is undefined. So I'm going to give you a curve, and I'm going to ask you to tell me the range of values of x for which the gradient is negative, the range of values of x for which the gradient is positive, and when is the gradient stationary. So example, let's say y is equal to x squared minus 7x. Y is equal to x squared minus 7x plus 5. Now what I want to do is find the range of values Find range of values of x where the gradient is negative, positive, and stationary. So to find the range of values of x for which the gradient is negative, positive, and stationary. So now first thing we have to do is find dy by dx. So if y is equal to x squared minus 7x plus 5, then dy by dx is equal to 2x minus 7. If dy by dx is equal to 2x minus 7, right? Now we want when the gradient is negative. So this is for where gradient is negative. Where gradient is negative. So where gradient is negative. The gradient is negative when dy by dx is less than 0. So what we're solving is when dy by dx is less than 0, which implies that whenever 2x minus 7 is less than 0, which is whenever 2x is less than 7, which implies that whenever x is less than 3.5. So for all x values that is less than 3.5, the gradient is negative. So the gradient is negative whenever x is less than 3.5. Now let's say now we want to find where the gradient is positive. So where the gradient is positive, so the second part, where the gradient is positive, now the gradient is positive when dy by dx is greater than 0. That's when the gradient is positive, which implies that we're solving when 2x minus 7 is greater than 0. And so the gradient is positive when 2x is greater than 7, which is when x is greater than 3.5. That's when the gradient is positive, when x is greater than 3.5. So let's say we want when the gradient is negative now. No, we'll find that. Let's say we want when the gradient is stationary. So when the function is stationary. So we can say at stationary point, at stat point, at the stationary point, dy by dx is equal to 0. So dy by dx is equal to 0 at the stationary point, which is implying that we're solving 2x minus 7 equal to 0, which is implying that x equal to 3.5. So when x equal to 3.5, or 7 over 2, let's write it as 7 over 2, then this is the stationary point, when x is 7 over 2. Now let's say now, this only gives us this just gives us one ordinate, and we know that x and y occur as a pair for the coordinates, right? And so we need to find the y value at the stationary point. And so we look back at the function, and the function is y is x squared minus 7x plus 5. When you get that value at the stationary point, you plug this x value back into the function. And so we get y is equal to, we plug in 7 over 2 squared minus 7 times 7 over 2 plus 5. And so that's how we get the y value. So let's plug this in our calculator. So we plug this in our calculator, and we're going to get 7 over 2 squared minus 7 times 7 over 2 plus 5. And we're getting minus 7 and a quarter. So we get minus 7 and a quarter. To write minus 7 and a quarter, we can write minus 29 over 4. Minus 29 over 4. So we can write minus 29 over 4. So that is the stationary point. Alright. So if you remember from CSEC days, the stationary point is what we call, at that time, we'd have learned it as the turning point. In CSEC days, we learn it as a turning point. So remember, we usually write a quadratic in the form a in bracket x minus h all square plus k. Alright, where hk was the coordinate of the turning point. Well, that's pretty much it. We just found the stationary point. It is turning right there, stationary point. So let's say I ask you to sketch this function now, right? So let's say we're going to sketch this. I'm going to show you what happened. So what happened now is we have the curve y equal to x squared minus 7x plus 5. And so we had the turning point, which we said was 3.5. So we look for the x value of 3.5 and a y value of minus 7. Minus 7 and a quarter. So we'll put it right here. This is the turning point. And it goes like this and it passes through 5. Right? Now, everywhere over here, the gradient is positive when x is greater than 3.5, because if you were to draw a tangent line at any point over here, you will get that the gradient is positive. Now over here, this side, the gradient is negative. So from here, gradient is negative, 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 negative. Then when it reaches here, turning point, here so the gradient is 0. And then up here, positive, positive, positive. Alright, almost look like a line, and think about it. The equation of this line would be negative. The gradient of this line would be negative. Here, so stationary, where the gradient is 0, where the gradient is equal to 0. Then over here, gradient is positive. And so that is this is how we use differentiation to tell where the gradient is positive, negative, or equal to 0. Now, let's say I did ask you to find the gradient at a point. Let's say I give you a curve y equal to x cubed minus 3x squared plus 2x minus 1. And I say, find the gradient when x equal 1. Find the gradient when x equal 1. Find the gradient when x equal 1. To find the gradient when x equal 1, all we have to do is find dy by dx, and that's equal to 3x squared. So we carry down the power, subtract 1 from the power, minus, we carry down the power, then we subtract 1 from the power to get x, carry down the power 1, subtract 1 from the power, we get 2. So this is the gradient function. So dy by dx is the gradient function. Now they want the gradient when x is 1. So all you're going to say is now when x equal 1, dy by dx is equal to, you're going to substitute the value for x equal 1 into the gradient function. So we're going to get 3 times 1 squared minus 6 times 1 plus 2. And that gives you the value of the gradient at that point. So 3 times 1, you don't need the calculator. 3 times 1 is 3. 3 plus 2 is 5. 5 times 5 minus 6 is negative 1. And so the gradient of the curve is equal to negative 1. That's the gradient of the curve. So the gradient of the curve is equal to negative 1. The gradient of the curve is equal to negative 1. Alright, nice. So that's the gradient of the curve. Alright, now we found the gradient of the curve. Now, the next thing that we're going to look at is what we call the nature of the derivatives. Alright, and we're going to start with the first derivative. So we looked at the derivative And we said that when dy by dx equal to 0, what happens right there? It's a stationary point, right? It's a stationary point. Now, at a stationary point, many things can happen. At a stationary point, it either means that the function is maximum at a maximum point, or the function is at a minimum point. Let me show you why. If you were to consider a quadratic function, a quadratic function takes this shape. This is the shape of a quadratic, right? At this point, it would be a minimum point, right? No matter where the axis is, this would be a minimum point, meaning this is the lowest point on the graph, so it's a minimum point. Now, if the quadratic shape like this, then this would be a maximum point. This would be a maximum point, right? Now, we can be able to determine whenever the function is a minimum point and whenever the function is a maximum point. We need to be able to deduce when it's a minimum point and when it's a maximum point. Differentiation allows us to do that. Now, imagine you have a function that looks like this, right? It has a maximum and it has a minimum. And so differentiation will enable us to find where is the maximum point and where is the minimum point. Alright, so that's what we're going to look at now. Alright, so let's write it down. So when dy by dx equal to 0, we have stationary point. Stationary point or points. Stationary points or points. Alright, so we have stationary points for whenever dy by dx is equal to 0. Now we have what is known as the second derivative. Second derivative. Now the second derivative of a function is d2y by dx squared, and d2y by dx squared, it's equal to d by dx, it's equal to the differential of dy by dx. So this is the second derivative. It just means we differentiate the first derivative. So we differentiate 2 times to get the second derivative. Now when d2y by dx squared is greater than 0, whenever it's greater than 0, then we have a max point, and whenever d2y by dx squared is less than 0, we have a minimum point. So whenever d2y by dx squared is greater than 0, whenever d2y by dx squared is greater than 0, we have minimum point, and when d2y by dx squared is less than 0, we have a maximum point. So that's it. Whenever the second derivative is greater than 0, we have a minimum point. Whenever the second derivative is less than 0, then we have a maximum point. Alright? So let's go ahead and see how we'd use that in a question. So a typical CAPE question might be something like this. A typical CAPE question might say, y, so given y is equal to x cubed, given y is equal to x cubed minus 3x squared plus 2, it says find all stationary points, and determine their nature. So this is a typical CAPE question. They say y is equal to x cubed minus 3x squared plus 2, and they say find all stationary points and then determine their nature. So to find the stationary points, we solve dy by dx equal 0. So we solve dy by dx equal to 0. So for a stationary point, or what we can write is at stationary point. So at stationary point, dy by dx equals 0. That happens at the start point. At the stationary point, dy by dx equals 0. So first thing we need to do is find dy by dx. So dy by dx is equal to 3x squared, carry down the power 3, subtract 1 from the power, minus carry down the power 2, we get 6, subtract 1 from the power, we get x. And so 3x squared minus 6x equals 0. Alright, so we're solving 3x squared minus 6x equals 0. Now solving this equals 0, I can factorize 3x to get x minus 2 equals 0. So I'm pretty much solving 3x equals 0 and x minus 2 equals 0. So I'm getting x equals 0 or x equals 2. Alright, so there are two stationary points, x equals 0 and x equals 2. Then the next thing is x equals 0 must correspond to a particular y coordinate. Now since this is the equation for y, I can go ahead and find the y coordinate. The y coordinate is going to be plug 0 into this equation to get 0 cubed minus 3 times 0 plus 2, and so y equals 2. That's how I get y. And so one stationary point is 0, 2. Now the next one for y is I can plug 2 into this equation. So I plug 2 into this equation to get 2 cubed minus 3 times 2 squared plus 2, and I'm getting negative 2. So I'm getting negative 2. And so this is the point 2, negative 2. 2, negative 2. Alright? 2, negative 2. Now, we need to determine the nature of these two stationary points. So now that we've found the stationary point, we need to determine their nature. Now remember what we said about their nature. When the second derivative is less than 0, then what we say? We say that the function has a maximum point. And when the second derivative is greater than 0, we say that it has a minimum point. So first thing we need to do is find where is the max point and where is the min point. So first thing, dy by dx is 3x squared minus 6x. And so d2y by dx squared is equal to, so d2y by dx squared is equal to 3x squared minus 6x. 3x squared minus 6x. When we differentiate 3x squared, we bring down the power, so we get 6, subtract 1 from the power, x minus 6. So that's the second derivative. The second derivative is 6x minus 6. Now, when x equals 0, what happened? The second derivative is 0 minus 6, which is negative 6. So the second derivative is equal to 6 times 0 minus 6, which is negative 6. And so what happens at this point? And so 0, 2 is a, remember when it is negative, it is a maximum point. So 0, 2 is a maximum point. So 0, 2 is a maximum point. Alright? Now, we need the next The next point was 2, negative 2. And so at when x is 2 now, when x equal 2, we get d2y by dx squared is equal to 6 times 2 minus 6, which is equal to 6, which is greater than 0. And so the point 2, negative 2 is a minimum point. Minimum point. Alright. So now we have the two stationary points, and we know which one is maximum and which one is minimum. The next thing they might ask you to do is sketch this curve. We have all the information we need to sketch this curve. So let's go ahead and sketch this curve. So y equal to 3x squared. Y equal x cubed minus 3x. So this was the curve again, y equal to x cubed minus 3x squared plus 2. Alright, so we're going to go ahead and sketch this curve now. So to sketch this curve now, remember it have a maximum point. Remember, these are information that we know. Maximum point is 0, 2. Minimum point is 2, negative 2. We also know where it cuts the y-axis. It cuts the y-axis at 0, 2. So it cuts the y-axis at 0, 2. So this is the y-intercept. Y-intercept 0, 2. The only other information we could want to make the graph a little perfect is to find the roots. And to find the roots, we would solve this cubic equation equal to 0. But we're not looking at that right now. So we're just going to sketch this curve now. So no maximum point or no minimum point. So the curve looks something like this. Alright? I like to sketch the curve first before I put in my axis. So after I sketch the curve, then I put in my axis. Now I put in my axis. Why I do that? Because it's easier that way. Because remember, right here is the minimum point, and you're going to have to label your point. The minimum point is 2, negative 2. So this is the point 2, negative 2. This is 2. This is negative 2. This is the point 0, 2. And this is the maximum point. This is the minimum point. And this is your graph of y equal x cubed minus 3x squared plus 2. Alright? And that would be how you would sketch the curve y equal x cubed minus 3x squared plus 2. Don't worry, I will leave some question for you to do as well. Alright. So this is how we determine the nature of stationary point. Stationary point can either be a local maximum or a local minimum. And another thing that stationary can be is what is known as a saddle point. It's a saddle point. It's a saddle point or a point of inflection when d2y by dx squared is equal to 0. So whenever the second derivative is equal to 0, it is a point of inflection or what is known as a saddle point. So, for example, let's say we have, let's look at an example of a point of inflection. Point of inflection really means, or saddle point, it really means that the function has a maximum and a minimum point at the same place. That's what that means. So for example, let's say y equal x cubed. So y is equal to x cubed. If y is equal to x cubed, then dy by dx is equal to 3x squared. And at the stationary point, we solve dy by dx equals 0. So we're going to solve 3x squared equals 0, and so we get x equals 0. Now when x equals 0, y is also going to be 0. And so 0, 0 is our stationary point. Now look at this now. Let's say we want to find the nature of this turning point. Now d2y by dx squared is, when we differentiate 3x squared, we're getting 6x. Now when x is 0, at x equals 0, we have d2y by dx squared is equal to 6 times 0, which is equal to 0. Now when it's greater than 0, it's a maximum. When it's greater than 0, minimum. Less than 0, maximum. Now look at this. This is equal to 0, so we don't know nothing about this. Alright? So this is now known as a point of inflection. When it's equal to 0, it means it's a maximum and a minimum point at the same time. So if I were to sketch the graph of y equal x cubed for you, this is how it looks. So the graph of y equal x cubed looks like this. So look what happened. Right here, it's going, then it turned right here. This is a stationary point, 0, 0. But it turned and it looked like it's going to be a maximum point. But then it just make a U-turn. Right? You see that? So right here, say it look like it'll be a maximum point. But then right here, say it look like it'll be a minimum point. Because you know, this is minimum point. And then this will be maximum point. So if you cut off this piece and cut off this piece, we end up with a portion where it's going to be a maximum and a minimum. I'll connect them together, and so what we get now is a function that is called a point of inflection. It has a maximum and a minimum at the same place, and so it is known as a point of inflection or a saddle point. Saddle point, point of inflection. Alright. And so that takes care of that. Alright. Now, the final thing that we're going to be reviewing for differentiation is applications of differentiation. Applications of differentiation is used in real life. Alright, so we use it in many things, like whenever we're talking about volume, whenever we're talking about areas, any little thing in real life we use differentiation, right? Mathematics is not just done on the board, but it is utilized in real world. Every topic in mathematics. Alright? And so now let's look at a practical application of differentiation. And the practical application that we use is known as what's known as chain rule. So chain rule, right now, look at it this way now. So look what I'm going to say. Now dy by dx can be equal to dy by a new variable, any new variable. It could be r times dr by dx. This is known as connected rates of change, or connected chain rule, where dy by dx is dy by dr times dr by dx. Now where does this come in from? Think about it this way. If we're to multiply them, right, this dr actually cancels this dr, right, and so it still works out back to be dy by dx, right? And so sometimes we may not know dy by dx, but we may know dy by another variable r and another variable r, dr by dx. So then we can use the connection between those two by multiplying them to find dy by dx. So let me write down an example. So let's say the area of a circle is given by A, and the area of a circle is given by A, and so the area of a circle is given by A, and the radius of the circle is given by R, right? So the area of the circle is given by A, and the radius of the circle is given by R. Now given that when R is equal to 2, given that when R is equal to 2, we have dx by dr is equal to 0.5. So find dA by dx when r equal to. So look what this question says. It says the area of a circle is given by A, and the radius of the circle is given by R. Given that when R equal 2, we have dx by dr equals 0.5. Find dA by dx. So I just made this question up out of my head. So the calculation might be a little bit rough because I randomly made this question. But let's have a look at it. Now, first and foremost, what is the area of a circle? The area of a circle, as we know it, so the area of a circle is given by area of a circle is equal to pi r squared. That's the area of a circle. Area of a circle is pi r squared. Now, the area of a circle is pi r squared, and so what that is telling me is that dA by dr is equal to, I can differentiate A with respect to R. Now A, think of it as a Y and R as a X. So I can carry down the power to get 2, subtract 1 from the power to get pi times the different times R. So that's dA by dr. So dA by dr is 2 pi R. Now what the question wants is dA by dx. So look what I'm going to find dA by dx. Alright? So dA by dx is equal to dA by dr times dr by dx. Makes sense, no? dA by dr times dr dx. And that's how we're going to find dA by dx. And so dA by dx is going to be equal to dA by dr. Now dA by dr is 2 pi r, but it's 2 pi r, but r is 2. Remember, it is when r is 2, so we can substitute for r 2. So it becomes 2 pi times 2 times dr by dx. Now look at this, dx by dr is 0.5, and so dr by dx is equal to 1 divided by dx dr. dx by dr is 0.5, and so dr by dx is 1 divided by dx dr. And so dr by dx is 1 divided by 0.5, which is 2. And so dA by dx works out to be 2 pi times 2 times 2. 2 times 2 is 4, 4 times 2 is 8. And so dA by dx works out to be 8 pi. This is known as connected rates of change. Alright, this is a practical application of differentiation as it relates to circles. Alright, easy. So we're going to take a few and then we look at part 2, where part 2 is where we're going to be looking at differentiating exponential functions, log functions, inverse trig functions, etc.